Good afternoon. Abuni and I would be presenting a fault-tolerant control system to address elevator jamming faults. This is the outline of our presentation. In this presentation, we will be focusing on addressing the aircraft actuator jamming. Actuator jamming is attributed to a permanent jamming and temporary jamming, in which their fault phenomena could be very similar. Hence, a conventional fault detection module cannot discriminate between them. Therefore, we propose a reconfigurable model prediction controller with an active fault detection module to address this issue.
Have you ever wondered what is responsible for changing the pitch of airplanes? Elevators are surfaces of flight control, typically at the rear of an aircraft to control the pitch of the plane, the angle of attack, and the wing lift. The pitch of an aircraft is controlled by adjusting the angle and therefore the lift force of the elevator. Lots of work have been done in the past to control the pitch of an aircraft for the purpose of flight stability. And yet this research still remains an open issue in the present and future works. So what is our motivation? In the past 2 decades, about 59% of the fatal airline aircraft accidents were caused by loss of control in flight. The malfunction or jam of aircraft control surfaces such as elevators are very dangerous because they result in a reduction of control authority and impose persistent disturbances on the aircraft. The most critical lactation device is the longitudinal aircraft control, and its failures will result in a catastrophic aircraft crash. In this presentation, we focus on the longitudinal control of an Airbus passenger aircraft in the presence of elevator jamming faults. We propose the use of Model Predictive Control, also known as MPC, as a fault-tolerant controller to actively help the fault detection unit discriminate between permanent and temporary jamming faults while ensuring the performance of the aircraft. Alright, let's dive into the more technical part of this presentation. I'll start off by explaining the mathematical representation of the aircraft longitudinal model. So the aircraft longitudinal model has 2 equations that are being used to calculate things. The first one is the linearized longitudinal dynamic of the aircraft, which is this equation 1a. And in this equation, x stands for the state vector, which could either be the pitch rate, the roll rate, the ground speed, the angle of attack, the pitch angle, or the altitude. And u here stands for the control input, and a and b are just constants. And this second equation stands for the discretized longitudinal dynamics of the aircraft, where y stands for the output and u is also the control input. As you can see, these other 2 equations basically mimic the first 2. Fault description. When elevators get jammed, one or more of them remains at fixed, unpredictable values. This might differ from their normal saturation limits. Elevator jamming can be attributed to 2 different root causes. The first one is known as the stock fault. This is also known as a permanent jamming. So once the elevator gets stuck in a certain position, it remains in this position and cannot be recovered. So from the graph, you can see this is where the jamming happened. This is where the fault started. And although this command was run, nothing happened. The elevator is still stuck in this position. And the second type of jamming is called the stall load. And this is basically like a temporary type of jamming. So we can see that here, the stall load started, and after this command is run, the elevator position is stuck for a certain time and we reach the end of the stall load where it gets recovered. Because of the similarities in these two jamming, it's hard to predict if it's a stock fault or a stall load. Hence, we propose our integrated fault-tolerant approach that actively modifies the control strategies to help the fault detector module discriminate between the two causes of the jamming.
The fault-tolerant control we are using is shown in the figure. In this diagram, we can see that the red box is the main component of the plant, and the green boxes are the main components of our fault-tolerant controller. Elevator state observer. As shown by the red line, we can see that the elevator state estimates are needed to exploit the elevator dynamics in the MPC formulation. On the other hand, the elevator state estimate are used to compute the predicted elevator outputs for the disturbance observer and FD module, which is shown by the yellow line. Disturbance observer. The disturbance observer strongly relies on the information provided by the MPC controller and on the plant measurements. The observer is composed of two modules. The first module uses the three equations shown on the slide. The first equation calculates the mismatch between the measured and predicted load factor. The second equation calculates the mismatch between the measured and predicted elevator outputs. Then, using the two mismatch we found, we can calculate the disturbance observer estimate by equation 3. The second module of the disturbance observer takes into account of plant model mismatch. We define an upper bound on these plant model mismatches, where xt hat is the measured state of the aircraft at time t. Xt is the value of state at time t predicted by measured state at t minus 1. This upper bound monitors the distance between the predicted behavior of the plant and the real behavior. As mentioned previously, we will be working with an active FD module with a MPC controller. This figure summarizes the interaction between the FD module and MPC controller. The fault detection is made by comparing each residual evaluation value indicated by Ji with the related threshold value. If Ji is less than threshold, then the elevator I is fault-free. If Ji is greater than threshold, then the elevator I is jammed. The threshold value will be determined by the plant model mismatch of the elevator model after fixing the slide window K. Ji is determined by its root mean square over the sliding window K. It takes into account of the elevator output predictor arrow and the slowest mode of actuator, which is to give sufficient time to the physical system to register the jamming fault. During the detection phase, the FD module constantly monitors each elevator. Once a fault is detected, the FD module sends a message to activate the first reconfiguration. The first reconfiguration is to help FD module understand the root cause of the jamming fault. The MPC will check if the upper or lower bound is at fault and modify it by a new bound. The new bound is indicated by the measured elevator position value at TF and a positive constant that is small enough to preserve the performance of controller but also large enough to allow the size of residual to exceed predefined threshold. With the modified bound, we compare Ji with threshold again. If Ji is greater than threshold, this means that the root cause is a stuck fault, since the elevator is unable to reach the tightened bound. If Ji is less than threshold within the diagnosed period, this means that the root cause is a stall load, since the jammed elevator can still move within the reduced bound. Once we diagnose the root cause of the jamming elevator, the FD module communicates with the MPC controller to activate the second reconfiguration. If a stuck fault is detected, the MPC performs the reconfiguration by setting the bounds according to the severity of the fault. If a stall load is detected, we first perform reconfiguration for the start of stall load by resetting the bound of the fault to a new value, which is not the original bound. This is to allow the detection of the end of stall load. During the reconfiguration for stall load start, the FD module constantly monitors the discrepancy between the measured elevator position and its previously jammed position. If the distance between them is less than alpha, that means the stall load is still active. On the other hand, if the distance between them is greater than alpha, the FD module communicates the end of the stall load to the controller and restores its original bound, then returns to monitor the residual value. In the case of a stuck fault simulation, we can see from the graph that by the end of the detection phase, the residual estimate, which is indicated by the blue curve, was still greater than the threshold. This indicates that this is a stuck fault. The MPC controller performs the reconfiguration for the stuck fault by updating the upper and lower bounds of the faulty elevators in the MPC problem formulation. As for the stall load simulation, on the residual evaluation plot, we can see that it is at fault since it reaches the threshold. However, by the end of the detection phase, we can see that the residual value is within the threshold. This indicates that it is a stall load. Even though the elevator is no longer installed by the end of the detection phase, the FD unit does not immediately declare the end of the stall load, since the curve was still close to the lower bound, which is smaller than alpha. Once the curve moves away from the bound, the stall load ends and it restores back to its original bound.
Now the question for you is, so do you think this system is completely reliable? As you might have already noticed, the proposed algorithm relies on the interactions between the FD unit and the MPC controller. The success of this algorithm mainly depends on the accuracy of the detection and the diagnosis. But what happens if one of these components fails? This may lead to the misdetection in the FD unit or misdiagnosis of a stock fault. And this misdetection can seriously affect the performance, especially if a stock fault is being diagnosed, because now the algorithm starts to act like the elevator is stuck when it's in fact perfectly healthy. An approach we're able to come up with to tackle the problem mentioned in the previous slide is hardware redundancy. Hardware redundancy is the most reliable way to increase the reliability of the system. Here, an actual component is installed in parallel to the main component, in this case the MPC and the FD, and the component performs the same function as the MPC or the FD. There are two major types of hardware redundancy, and the first one is known as the dual redundancy, which is shown here, and the second one is known as the triple modular redundancy, or the TMR redundancy. I'll go into more details, but this has already been covered in the lecture. In conclusion, we presented a novel fault-tolerant controller tailored to aerospace applications. Our approach relies on the close interaction between a fault detector module and a model predictive controller. The FD module exploits the controller to diagnose the root cause of the elevator jamming, and the MPC exploits the information from the fault detector module to better predict and handle the jamming. Although this approach proved to be highly reliable from the results, one concern we had was the stability of the FD and the MPC. We concluded that this issue could be resolved using hardware redundancy. These are the references we used for our presentation. Thank you for listening to our presentation. We'll now open the floor for questions.